This video is about the cross product. In this video, I'm going to cover some important theorems related to the cross product. And for each theorem or fact that I cover, I'm going to go over some example related to it. Let's start with the definition of the cross product. The cross product of vectors u with components u1, u2, u3, and v with components v1, v2, v3 is the vector u cross v, which is the 3 by 3 determinant. The first row of our determinant are the vectors I, j, k. The second row are the components of the first vector u. These are u1, u2, u3. And the third row of our determinant are the components of vector v, the second vector. These are v1, v2, v3. And when we compute the determinant, we wind up with this vector, which is the cross product u cross v. Let me remind you of how to compute a 3 by 3 determinant, particularly this determinant that we have for the definition of the cross product. There are different ways of computing a 3 by 3 determinant. One way is to expand along the first row. So what I'm going to do is I'm going to look at the entry in the top left corner, the entry I. I will cover everything in the row of I and everything in the column of I. When I do that, I'm left with this 2 by 2 determinant. So I write determinant u2, u3, v2, v3 times the vector I. That's the first step. The second step, I'm going to move along the first row to the second entry. This is the entry vector j. I'm going to cover everything in the row of j and everything in the column of j. I will be left with the 2 by 2 determinant u1, u3, v1, v3. So, minus, pay attention to the sign, it's a minus sign, not a plus sign. The 2 by 2 determinant u1, u3, v1, v3 times the vector j. I go further along the first row to the third entry, which is entry k. Cover everything in the row of k and everything in the column of k. We will be left with the 2 by 2 determinant u1, u2, v1, v2. Now, I have a plus the 2 by 2 determinant u1, u2, v1, v2 times the vector k. And keeping in mind that the determinant of a 2 by 2 matrix in general, A, B, C, D, we compute that by doing A times D minus B times C. So all of those 2 by 2 determinants are computed according to that rule. And when we compute these determinants, we get the cross product u cross v that I circled in green. Here's an example. Let's compute u cross v for the vectors u with components 1, 3, negative 5, and v with components 6, 6, 0. Let's write the determinant for u cross v. U cross v is the 3 by 3 determinant whose first row are the vectors I, j, k. The second row are the components of u, 1, 3, negative 5. And the third row are the components of v, 6, 6, 0. That's equal to the 2 by 2 determinant 3, negative 5, 6, 0 times the vector I minus the 2 by 2 determinant 1, negative 5, 6, 0 times the vector j plus the 2 by 2 determinant 1, 3, 6, 6 times the vector k. The determinant 3, negative 5, 6, 0 is obtained by doing 3 times 0, which is 0, minus 5 times 6, which is minus 30, all multiplied by the vector I, minus the second determinant, which is 1 times 0, that's 0, minus 5 times 6, which is minus 30. J plus the third determinant, which is 1 times 6, that's 6, minus 3 times 6, which is 18, times the vector k. That's equal to 30i minus 30j plus, minus 12k. And that is u cross v. This next theorem, the cross product theorem, tells us the direction of vector u cross v. Specifically, u cross v is orthogonal to both vectors u and v. Furthermore, the orthogonal direction of u cross v is given by the right-hand rule. The way this works is you point your right index finger in the direction of u, then you curl it toward v, and your right thumb, will point in the direction of u cross v. Here's an example. Find a vector that is orthogonal to both vector u with components 1, 1, 7 and vector v with components minus 6, 2, 3. One way to solve this problem is to invoke the cross product. We know by the cross product theorem that u cross v is orthogonal to both u and v. So if we can find the cross product, there we have a vector that is orthogonal to both u and v. So we'll write u cross v is orthogonal to both u and v. Let's find the cross product. It's the 3 by 3 determinant, whose first row is I, j, k. Second row, 1, 1, 7. And third row, minus 6, 2, 3. That's equal to the 2 by 2 determinant 1, 7, 2, 3 times the vector I minus the 2 by 2 determinant 1, 7 minus 6, 3 times the vector j plus the 2 by 2 determinant 1, 1 minus 6, 2 times the vector k. The determinant 1, 7, 2, 3 is given by multiplying 1 times 3, which is 3, minus 7 times 2, which is 14, minus the 2 by 2 determinant, which is 1 times 3, that's 3, minus 7 times 6, which is negative 42, times the vector j, plus the third determinant, which is 1 times 2, that's 2, minus 1 times negative 6, which is negative 6, all multiplied by the vector k. 3 minus 14, that is minus 11i, minus 3 plus 42, which is 45. So we have negative 45 times the vector j. 2 minus minus 6 is plus 8. So plus 8k. So the vector minus 11i minus 45j plus 8k is orthogonal to both vectors u and v. So far, we know that the cross product of u and v is orthogonal to both u and v. This next theorem tells us about the length of the vector that is the cross product of u and v. If theta is in the closed interval from 0 to pi is the angle between vectors u and v in R3, then the magnitude of the cross product u cross v is the magnitude of u times the magnitude of v times sine theta. Particularly, if u and v have the same or opposite directions, that is, theta is equal to 0 or pi radians, then the magnitude of the cross product is 0. Let's see an example. If the magnitude of u is 12 and the magnitude of v is 5 and the angle between u and v is 30 degrees, let us compute the magnitude of u cross v. We'll use the last theorem to do that. Magnitude of u cross v is the magnitude of u times the magnitude of v times the sine of the angle between them. So, u cross v is magnitude of u times magnitude of v times sine theta. That is 12 times 5 times sine of 30 degrees, which is 1/2. That's 6 times 5, which is 30. That is the magnitude of u cross v. Our next theorem is an interesting application of the cross product. Specifically, the magnitude of the cross product, u cross v, is the area of the parallelogram spanned by vectors u and v. Let's see an example. Find the area of the triangle with vertices P, whose coordinates are 1, 4, 6, Q, whose coordinates are 3, 0, 1, and R, whose coordinates 0, 0, negative 2. First thing to notice when solving this problem is that the area of triangle PQR is half of the area of the parallelogram spanned by vectors PQ and PR. This is illustrated in the picture in the top right of the screen. We also know from the previous theorem that the area of the parallelogram spanned by two vectors u and v is the magnitude of their cross product. So we're going to capitalize on this fact and on the fact that the triangle has half the area of the parallelogram to figure out the area of our triangle PQR. So we'll write area of triangle PQR is the magnitude of vector PQ crossed with vector PR divided by 2. Vector PQ is obtained by subtracting the components of P from the components of Q. That's 3 minus 1, that's 2. 0 minus 4, that's negative 4. And 1 minus 6, which is negative 5. Vector PR is obtained by subtracting the components of P from the components of R. That's 0 minus 1, which is negative 1. 0 minus 4, which is negative 4. And minus 2 minus 6, which is minus 8. Now let's compute the cross product PQ cross PR. That is the 3 by 3 determinant with first row I, J, K. Second row 2 minus 4 minus 5. And third row minus 1 minus 4 minus 8. That's equal to the 2 by 2 determinant minus 4 minus 5 minus 4 minus 8 times the vector I minus the 2 by 2 determinant 2 negative 5 minus 1 minus 8 times the vector J plus the 2 by 2 determinant 2 negative 4 negative 1 negative 4 times the vector K. That's equal to minus 4 times minus 8, which is 32, minus 5 times minus 4, which is plus 20, all multiplied by the vector I, minus 2 times minus 8, which is minus 16, minus 5 times minus 1, which is plus 5. All multiplied by the vector J, plus 2 times minus 4, which is minus 8, minus 4 times minus 1, which is plus 4. All multiplied by the vector K. That's equal to 12I minus 21 times minus gives us plus 21J minus 8 minus 4, that's minus 12K. So we have PQ cross PR is the vector 12I plus 21J minus 12K. Let's find the magnitude of this vector. Magnitude PQ cross PR is equal to the square root of 12 squared plus 21 squared plus minus 12 squared. That's equal to the square root of 729, which is equal to 27. The area of triangle PQR is the magnitude of PQ cross PR divided by 2. So, the area of triangle PQR is 27 divided by 2, which is 13.5. Finally, let's talk about the scalar triple product of three vectors. The scalar triple product of vectors u with components u1, u2, u3, v with components v1, v2, v3, and w with components w1, w2, w3 is the number defined by the 3 by 3 determinant, whose first row is u1, u2, u3, second row v1, v2, v3, and third row w1, w2, w3. Turns out that the scalar triple product has an interesting geometric meaning. Specifically, the absolute value of the scalar triple product u dot v cross w is none other than the volume of the parallelepiped spanned by the vectors u, v, and w. This is illustrated in the figure here. And that's vector v here. Here's an example. Show that the vectors u with components 1, 4, negative 7, v with components 2, negative 1, 4, and w with components 0, minus 9, 18 are coplanar, meaning all three vectors lie in the same plane. To show that these vectors lie in the same plane, we are going to show that the volume of the parallelepiped spanned by vectors u, v, and w is equal to 0. And recall that the volume of the parallelepiped spanned by u, v, and w is the magnitude of the scalar triple product. So let's compute the scalar triple product. U dot v cross w. This is the 3 by 3 determinant, whose first row is 1, 4, negative 7. Second row, 2, negative 1, 4. And third row, 0, minus 9, 18. That's equal to 1 times the 2 by 2 determinant, minus 1, 4, minus 9, 18, minus 4 times the 2 by 2 determinant, 2, 4, 0, 18, plus negative 7 times the 2 by 2 determinant, 2, negative 1, 0, negative 9. We have 1 times negative 1 times 18, that's negative 18, minus 4 times minus 9, which is minus 36. Minus 4 times 2 times 18, that's 36, minus 4 times 0, which is 0. Minus 7 times 2 times minus 9 is minus 18 minus 1 times 0, which is 0. That's equal to minus 18 plus 36, which is plus 18, minus 4 times 36, that's the same as 8 times 18, because 18 is half of 36, minus 7 times minus 18, that's plus 7 times 18. We have 18 times 1 minus 8 plus 7, that's 18 times 0, which is 0. This means that so we found that U dot V cross W equals 0, which means that the absolute value of U dot V cross W equals 0, but that's the volume of the parallelepiped spanned by U, V, and W. And since that volume is 0, it must be that the vectors U, V, and W are coplanar. They must all lie in the same plane.